All right, well, here we are at the beginning of chapter 6. In chapter 6, we basically go into greater depth applying Newton's laws, the laws that we learned in the last chapter. And some of them involve problem-solving approaches. Some of them just involve applying them to situations that are a little more complicated than we may have seen before. The first, it starts out with solving problems with Newton's laws. So it's basically laying out some strategies for applying Newton's laws to situations that are maybe a little more complicated than what we've seen so far. Some of the problem-solving strategies they recommend are listing the quantities given and any other quantities that may be known that are relevant to the problem, and also listing those that need to be found. Whether they need to be found because the problem is explicitly asking for them, or because they might need to be found because you need to find certain things in order to find what the problem is asking for. Then you want to, basically doing that identifies the physical principles involved. And once you know the physical principles that are involved, you can approach the problem much more easily, because that will bring in maybe in many cases a certain group of equations that can be applied to that type of problem. Now, of course, you want to draw a sketch using arrows for forces, identify the system. That is, what is it that you're going to be focusing on, and what is it, who is basically the part of the situation in which you're going to be accounting for all of the external forces on that part of the situation, and draw a free body diagram and use the second law to solve solve a problem using kinematic equations. And it's always a good idea at the end of any problem, not only problems like this, but, as I've said, even with something like unit conversions, always at the end stop to consider whether your answer is reasonable. In dealing with things like Newton's that we're not that used to dealing with, it may not be that easy to determine whether the answer is reasonable or not. But in dealing with things that we're more familiar with, like simple unit conversions, then you usually can judge whether it's reasonable or not. But one thing to watch out for, and one thing that will help in whether the answer is reasonable or not, is, do the units work out? Because if the units don't work out, then the answer is wrong, even if the number seems reasonable. And if the units do work out, then the answer is probably right. Because, as long as you've been careful along the way, if you get the units to work out correctly, then you've probably used the right numbers and you've probably done the right things to them. Okay, because if you're watching the units all along, and if you're essentially doing the same things with the units as you're doing with the numbers when you multiply and divide, then getting the right units should mean getting the right number too. And it usually does. An example of applying these rules is the example of lifting a grand piano into a second-story window. The figure is on page 267 if you want to look at it directly. It basically, they've got a grand piano. It doesn't look like a grand piano because it's basically wrapped in a tarp and it's on its side on and being lifted by a crane into a second-story window. But we want to look to see whether there are any forces involved, and certainly lifting something that heavy up to a second floor window definitely involves forces, and that would mean that Newton's laws apply. And then we can draw a sketch with arrows, and my artistic ability sucks, so I'm not going to draw a sketch, but I will draw a free body diagram. And the free body diagram, again, just uses a point for the center of mass of the object. The system in this case is the piano itself, and we're lifting it with a line from a crane, and so there will be tension in the line, and that will be counteracted by the weight of the grand piano pressing downward. since the situation that's shown in the picture is the piano just sort of hanging there, about to go through the window, but not actually going through the window, the net external force would be 0 at that point because the piano is not accelerating in any direction. In fact, at that moment, it's not moving in any direction either. So what that means is that the magnitude of the tension must be the same as the magnitude of the weight, or because there's no net force in the vertical direction, no net force in the horizontal direction either, but we're concerned more about the vertical direction. And that would mean that the tension in the wire or the line is equal to the negative of the weight in mathematical terms. Ft in the diagram is a downward force that the piano exerts on the rope, but that's an internal force and is therefore ignored because it's a force that's being exerted by the piano, which is the system in this case, on the surroundings. So again, we ignore that. You can assume that any other forces like friction or wind or anything like that would be very small, mostly because they weren't mentioned. If they were significant enough for us to take them into account, then we would have to be given some idea of their magnitude. So we want to list all the knowns and the unknowns, and then you can apply the second law to the free body diagram. In this problem is actually one-dimensional in the vertical direction, tension pulling up, weight pulling down, and so it can be handled algebraically. You wouldn't even really need to bring in vectors or anything like that to any great degree. If the problem were 2 or 3 dimensional, then you would have to break down each dimension into a one-dimensional problem with setting out the axes and the components, and then you can use the component versions of Newton's second law. That is, the summation of all of the forces in the x direction is equal to the mass times the acceleration in the x direction, and so on. And of course, check to see if the solution is reasonable, and check the units of the answer to make sure that they work out correctly. Remember that a Newton is a kilogram times meters over seconds squared. And so that a lot of times, otherwise, when you have calculations involving newtons, it can get kind of confusing whether the units actually work out or not. But if you remember this, then you can make sure that the units work out correctly. Okay, so they're looking at objects. You can have an object that's in equilibrium or an object that's not in equilibrium. Physicists tend to use the word particle. I personally don't like that because, to me as a chemist anyway, particle tends to imply that something is really small. But in physics, it doesn't necessarily mean that it's really small. Particle in physics could be quite large. So let's just think, when we say particle, think object. A particle is in equilibrium if all of the outside forces on it are balanced. Okay. And if you remember, what we've been saying all along is that balanced forces mean no net force, and no net force means no acceleration. So that's what we really mean here. A particle in equilibrium is one that has no acceleration. There are a couple different types of equilibrium, though. There's static equilibrium, static meaning standing still, and that would be for a particle at rest. And a particle at rest does have 0 acceleration, and it also has 0 velocity. But then there's also dynamic equilibrium, dynamic meaning moving, and that would be a particle in motion. But a particle in motion with a constant velocity and therefore 0 acceleration. So it's just going back to that old reminder that constant velocity could mean zero velocity, because being at rest is also an example of constant velocity. So static versus dynamic equilibrium. A way that Newton's laws can be applied would be finding tensions in when something is hanging from a wire or a cord, when the angles by which the cord is deflected on the two sides are not equal to each other. We saw examples in the last chapter, a couple examples where the angles at both ends of the cord were equal to each other, and that's pretty easy to work out. But what if they're not equal to each other? So in this case, you've got a 15 kilogram traffic light that's suspended from two wires, and we want to find the tension in each wire, and you can neglect the mass of the wires themselves just to make things a little simpler. Okay, so we've got a traffic signal with its little three lights in it, and it's hanging closer to one pole than the other, so that the angle on the right-hand side is 45 degrees, and the angle on the left-hand side is 30 degrees to the horizontal. In each case, you've got a tension in the lines, and I'm going to call tension 1 will be the tension in the line to the left, and tension 2 will be the tension in the line to the right. And you've also got the weight of the light itself, which is pulling straight downward. In this situation, we first want to choose what the system is going to be, and it would make the most sense to choose the light itself as the system. That makes it easier than any of the other possibilities. Okay, so once you've chosen that the light itself is going to be the system, you can focus just on the forces on the system. That is, forces imposed from the outside on the system. So you've got the weight that's imposed by gravity from the outside on the light. So you've still got the weight pulling straight down. And you've got T1, the tension in the line on the left, pulling up at an angle to the left. And you've got T2, the tension in the line to the right, pulling up and at an angle to the right. Looking at a free body diagram of that, you could represent the light itself as a point, and you have weight pulling straight down, and T1 going off at an angle to the upward and to the left, and T2 going off at an angle upward to the right. In this case, no two vectors are parallel to each other, so we might as well go ahead and just use the customary axes, where X is horizontal and Y is vertical. That way, W is entirely in the Y direction, but for T1 and T2, we're going to have to find their components. So again, using the axes and finding components, we've got the weight pulling straight downward, which is entirely along the Y-axis. But for T2, we would have to resolve the force into Y component and X component. So T2X and T2Y. And then for tension number 1, going off to the left, we would have to resolve that into T1X and T1Y, the X and Y components. And then once we've done that, we could draw the free body diagram again, where the light again is just that point in the center. And then we have the weight still pulling straight downward. And we have the X component of T1 pulling straight to the left along the X-axis, and the X component of T2 pulling straight to the right along the X-axis. And then we have T1, that is the Y component of T1 and the Y component of T2, both pulling upward in the Y direction. And so that's why we draw two arrows head to tail. The net force on this system, because the light is not accelerating up or down, or to the left or to the right, the net force has to be 0 in the x direction, and also the net force is 0 in the y direction. And what that means is what I've written mathematically down here, that you have weight pulling straight downward in the y direction. You have the y components of tension 1 and tension 2 pulling straight upwards in the opposite direction. So since there is 0 net force in the y direction, that would mean that T1y plus T2y must be equal in magnitude to W. Or in numerical terms, T1y plus T2y must be equal to negative W when you include the direction. Also, because there's no net acceleration in the x direction, that would mean that the net force in the x direction must be 0. And that would imply that the x component of T1 must be the same magnitude as the x component of T2, but they're in opposite directions. So mathematically, T1x is equal to negative T2x. Okay. What we want to find would be T1 and T2. So you've got two unknowns essentially in this situation. And so you're going to need two equations. So we use the second law along the x and y axes, where the net external force would be 0 in both directions. For the x-axis, you can say the net force in the x direction is equal to T2x, that is the x component of T2, minus T1x, that is the x component of T1, and that equals 0. So in other words, T2x equals T1x, at least in terms of magnitude. And that would mean that, well, the x component of T1 is T1 cosine 30, because 30 is the angle that's associated with T1. And T2, the x component of T2 would be T2 times cosine 45, because 45 degrees is the angle associated with T2. And then if you just want to solve for T2 in terms of T1, you can just rearrange this equation, divide both sides by the cosine of 45, and you get T2 is equal to T1 times the cosine 30 over the cosine of 45. Those are numbers that you can calculate. So cosine 30 over cosine 45 is equal to 1.225. So T2 is equal to 1.225 T1. This is what you normally do when you have two equations with two unknowns. You take one of the equations and you find, basically solve for one of the unknowns in terms of the other unknown. And then you insert it back in the equation. For the y-axis, we know that the net force in the y direction has to be 0, because the light is not accelerating in the y direction. And so tension 1 plus tension 2 must be equal to the negative of the weight. The same magnitude, but in opposite directions. Or in terms of magnitudes, you could just say T1 plus T2 equals the weight in the y direction. Sorry, those should have y's after them. Okay, so the y component for T1 is going to be magnitude of T1 times sine of 30. The y component of T2 is going to be the magnitude of T2 times the sine of 45, and that's equal to W. We can then substitute for T2 in terms of T1 up here. So basically you take 1.225 T1 and put that in place of T2 down here, and what you get is T1 times 0.5, that's the sine of 30, plus 1.225 T1, that is T2, times 0.707, that's the sine of 45. And that equals W, W of course being mass times gravity. Okay, working this out and simplifying it a little bit, we get 0.5 T1 plus 1.225 times 0.707 is 0.866. So that's 0.5 T1 plus 0.866 T1, which is 1.366 T1, is equal to 15 kilograms times 9.8 meters per second squared. That's 147 newtons. So 1.366 T1 equals 147 newtons. T1 would then be 147 newtons divided by 1.366. That's 107.6 newtons for T1. For T2, well, that's 1.225 times T1. So 1.225 times 107.6 is 131.8. So T2 has greater tension in the line than T1 does because it's at a steeper angle. So again, it's a lot of algebra involved here. Actually, it's, you know, like I said, when you have two equations and two unknowns, the first thing to do is solve for one of the unknowns in terms of the other unknown, and then substitute that in for the second unknown, so that you only have one unknown in the equation, and then you can solve the equations. Okay, that was particles at equilibrium. This is particles or objects undergoing acceleration. If a particle or an object is accelerating, then that means, acceleration. If the particle or object is accelerating, then that means that the net force in the direction of acceleration is not zero. Okay. As a practical example of this, we're going to try to figure out what the drag force is on a barge. The drag force just being, you know, the drag force is just another name for friction, but in specifically it's friction applied by fluids, like say air or water or some other liquid medium. Friction in physics anyway tends to be used exclusively with solids. You know, solid surfaces exert friction, while air or water exert drag. But the concept is essentially the same. It's a force that opposes motion. And so it's a force whose direction will be directly opposite the direction of motion, or the, you know, direction of potential motion. In this case, we have two tugboats pushing on a barge at different angles. And I drew a little sketch here. The big rectangle is the barge. And you've got one tugboat pushing directly in the X direction. And you've got another tugboat pushing perpendicularly to it. They push with different amounts of force, though, and that results in the barge moving off at an angle, not along the X or the Y axes exactly. So tugboat one pushes with a force of 270,000 newtons in the X direction, or 2 times 10 to the fifth, 2.7 times 10 to the fifth. That's 270,000. Tugboat two pushes with a force of 3.6 times 10 to the fifth, or 360,000 newtons in the Y direction. And the mass of the barge is 5 million kilograms, 5 times 10 to the sixth. The acceleration of the barge is 7.5 times 10 to the minus 2 meters per second squared, or 0.075 meters per second squared. Because of the way the diagram is drawn, we kind of know ahead of time that this is occurring at an angle of 53.1 degrees to the x-axis. But we don't necessarily need to know that in order to do this problem. In fact, we can very easily find that angle from the information that we're going to develop along the way. Okay, so what is the diagonal force of the water on the, or sorry, not diagonal, I can't read my own writing, drag force of the water on the barge. That's what we want to find out. And to do that, we're going to have to draw a free body diagram and then do some geometry. I see that, yeah, we're about up to time on this segment of the video. So I'm going to cut this example here and we'll come back and we'll start drawing the diagrams once we continue.